will tell us about CaDiCaL and proof logging in that solver, please.
Yes, so I will close the circle and come back to be at the very end of my talk. And it will be a little bit chaotic because I got some new ideas during the first day of Whoops and I kind of integrated them yesterday evening. So you'll see some slides which were definitely created with lots of care. Right, we're talking about CaDiCaL, so we want to do proof logging for standalone SAT servers. Well, my work starting out in this entire thing is implementing LRAD. I'm not the only person that implemented LRAD for CaDiCaL in this room, but let's set this aside. So this was my work starting out. And of course, well, we saw some examples yesterday, I think, where you should all know we kind of have the root semantics, and then we can annotate it with hints, and then we can check it a lot faster. We get this trade-off between engineering effort in the solver and then the checking speed at the end. This, I claim, turns out to be a good trade in SAT solvers. So you can certainly do this for mini-SAT. We got the remark yesterday, if you do it in mini-SAT, it's really simple. And it turns out like these trades are so necessary for PB and all of the very PB paradigms. So I think we got a paper at CP this year where they implemented lots and lots of engineering tricks to make proof checking actually feasible in practice. So first, really nice slides. I hope you can read my handwriting. So I have a very small example of an implication graph, which is supposed to depict the run of the CaDiCaL algorithm at a certain state where we where we have a conflict, and then we have decision levels. Okay, I think my example is slightly wrong. So E was supposed to be a unit, but here it's kind of not in the formula. So you can pretend it's a decision, and then the levels move by one, but the example still works. So what does the implication graph say? Well, we have a lot of nodes, and each node is a clause. And actually, each node is also an assignment in the solver. We can either have decisions or like reasons. And then when we do our conflict analysis, we want to resolve a bunch of clauses to derive a new one, which is actually propagating. So usually the property we're looking for is this first UIP, or actually any UIP. So we perform our conflict analysis from the conflict node backwards in topological order, and then we stop when we reach the first UIP, which we can do by counting the number of open nodes on this level. And if we do that, we get a resolution proof. So this is really nice. We can directly convert this to LRAD. So LRAD actually, it does not implement resolution proof semantics. It does the root semantics, which are slightly more general. So Jakob said it's kind of the same. There are some differences in practice, which we'll come back to next slide, I think. So, okay, we get a resolution proof for this first UIP clause by simply saying, okay, we resolve the conflict clause with this clause here, and then resolve also with this. Oh, I think it's just one. Is it? Maybe two resolution steps. Yeah. Now, well, if we want to do it in a sophisticated SAT solver, and I'm not sure if a mini SAT implements like minimization of the learned clause, we actually have some further algorithms that minimize our clause. So if we look at this lower decision level, we can easily see that, okay, if we now resolve with this binary clause here, we actually get rid of an entire literal in our learned clause, and this is good. So we want to do this, and there's a recursive algorithm. Actually, there are two different algorithms that do these minimizations. The issue with these algorithms is if you apply them and you want to compute LRAD proofs on the fly, suddenly you can't do it anymore. Yes.
Last is the diagram because I never understood how this analysis works, but I still don't. Yeah. Aren't the decisions here E, not A, and D?
Yes.
And shouldn't the conflict clause be a subset of these decisions?
No. Well, that's for DPLL, you get the conflict clause as a subset of the decision. Actually, in DPLL, you would just assume all of the decisions.
Okay, yeah.
Now, if you perform this conflict analysis backwards all the way to the decisions, then it turns out you can derive this decision only clause by resolution. You just don't stop at this first UIP. So this is an optimization where actually, you know, okay, I only care about that the clause will propagate once I backtrack. So I only care about this UIP property. And once I have derived a clause with this property, I can stop my conflict analysis. And that's usually better than doing more resolution steps, because usually you'll get longer clauses.
Which block off such space, yeah.
Yes.
Thank you.
As you said here, Florian, right? You would only take the conflict analysis here to get the first UIP. You just take the two clauses on row 2, guys, and you resolve them, and then immediately this one and the one to the right.
Yes.
And then you immediately get a first UIP because it only contains
Exactly.
F at the last level.
Exactly. Then you stop. And now, right, this recursive algorithm, it looks at lower levels and it will try to get rid of literals without incurring additional cost. And there's a modified version which also tries to shorten the clause, but it can actually change variables to do that. So
the one thing that I don't fully understand, like even with clause minimization, you still have a RUP clause. This is like a guarantee that.
Yes, it's the
So
RUP,
in principle, that means that look at that propagation, and that would be a LRAD proof. But you're saying it's like hard to extract that LRAD.
Yes. So by looking, okay, one thing, if you look at the final clause and then you look at the graph, it's very easy to reconstruct the LRAD proof. So, or the resolution proof. So this is kind of given in the solver. Okay, we get this final clause. We already have the graph, which was built during the search, and now we can compute the resolution proof. This is very easy. This is like a linear time algorithm somehow, where you get the order of the literals that you need to resolve. You have them on the trail, you can do it. Now you want to be slightly more clever and more efficient, which is why you kind of want to do it on the fly, right? There's no point in deriving this clause, doing exactly the algorithm I mentioned for deriving the resolution proof separately from the proof. So you want to combine it, and now there's the point where, okay, actually these minimization algorithms, you can't combine the proof and the derivation, because they will use some kind of backtracking, a depth first search, in order to determine like whether you can remove literals. So you can imagine here could be an arbitrarily long chain of binary implications, and I can still remove this literal, but I need to perform many resolutions to get it. So this is a recursive algorithm, but it can also fail, so you can't do the proof on the fly, because then you need to backtrack in the proof, and this would incur a lot of like bookkeeping overhead. So it's just easier and probably also faster to do it afterwards. So then for this entire thing, just combine the two approaches. As I said, it's very easy to get the LRAD proof for this one, and then you get the after the fact derivation of the proof between this difference, which is then again simple again to get the shorted clause, and you combine these two.
So would you get one LRAD line in the end, or would you do two, like one for the unminimized and then
You can get one. You can take this proof and compose it with this one. You need to be slightly careful. So there's already where the first difference between the root semantics and resolution semantics comes in. Actually, maybe like this clause depends on a lot of unit clauses. So just pretend we get many unit clauses that are fixed already, and they occur in all of the clauses. Then now, in order to derive this clause, we need to already resolve with some of our units. And if we then compute the proof for this clause or for the difference, we again need to resolve with some of our units. Now, if we simply compose our two proofs, we actually can have duplicate units. So it's not a resolution proof anymore. Well, it is if you take it the intermediate step. So if you get two LRAD lines, then it's still a valid resolution proof. But if you want to merge them into one line, which makes sense because this clause is never learned in the solver. So you want to have one line of the proof per clause that's learned in the solver, ideally, right?
You can fix it easily by putting all the rest of the units.
Yes, yeah, that's the trick again. So initially you disregard all the units while computing this proof. Then you compute the difference, again disregarding units, and then you collect all the units that you needed to do this. So you can come up with a formalism that computes a proof for conflict analysis, and I would agree with your statement that this should be very simple in Minisat, and also in CaDiCaL it's not too hard. So,
sorry, just one question. When you call it the clause minimized, does this also include shrinking?
yes. So here I don't really differentiate between the two, because the approach in any case is you look at the final clause and then you compute the difference. So it doesn't matter which algorithm you use to compute this, as long as it follows from the implication graph, which it should, right? What are the practical challenges then of computing LRAD? I already talked about the differences between group and resolution semantics. Okay, now we know we can use duplicate units in root proofs, or I told you, and the cake PB, no, the cake, there's checker, verified checker based on cake. I will agree that this is fine, I think. So now, do we actually want this, right? We actually are doing resolution proofs, and in case of CaDiCaL, every reasoning step we do is resolution. So why should we have the root semantics which don't directly map to our solver? Well, it's slightly easier to get valid proofs because you don't care about duplication, but then you kind of care about duplication because it increases the proof size. So here we just said, okay, we fixed the resolution semantics, and then we stay with that, which makes it, and Matthias can tell you, makes it way more involved to get valid proofs in the end. So not for conflict analysis, there you can kind of work around it, but there are other techniques, causal congruence closure, which is implemented in KISAT, and in not yet released versions of CaDiCaL, that's very a very different story. Yes.
Sorry, may I ask? I don't think I understand the difference between group and resolution semantics. Is it about whether what I call the accumulated formula is a set or a multiset? Or
No, so for resolution semantics, you can only apply the resolution rule, and you are not allowed to resolve over the same variable multiple times. So you start at the conflict, you take one clause, you resolve them, and you take the next one, and you can always get a resolution like this semantics, turn it around, and now you have a EuroProof, which is you negate the clause, and then you propagate all the antecedents, and then you get a conflict. But you can have things in the EuroProof that are not necessary. You can add literals to your learned clause, which are not necessary. So you can weaken the learned clause. The resolution, the result of your derivation is always exactly like the literals in the antecedent clauses. So you don't know. Yeah.
But then which one is the problematic? That's what I'm trying. So when implementing it in CaDiCaL, which one is
the problem, or it's easier to follow the RUP semantics, but for you want to have better proofs that are more usable, and that might be smaller because you're not doing unnecessary things. So you really want the resolution semantics. That's my point. So we stick to this because we think it's better.
We should try to move on.
Yes.
In the interest of time.
So, practical challenges, lots of algorithms let us do reasoning steps, all of them RUP, luckily, many implicit. So the general gist is, we track the relevant reasoning steps and reconstruct LRAT. Afterwards, to make it faster, we do on-the-fly computation as much as possible. And then here these last two bullet points. Maybe if I didn't go into CaDiCaL and implement LRAT, but instead I had this vision of I want to do a solver that produces resolution proofs, I might design algorithms differently. I don't know. I may also simplify algorithms in the sense that it makes it simpler to produce resolution proofs on the fly. And so this is kind of an open question, which I feel like, this approach of going into the solver afterwards to do the proofs is not always the best. So I have another example, and I will go through it very quickly because I spent way more time on the first example than I thought I would. So this is a binary implication graph. We have lots of binary clauses in our problem, and then actually many variables end up being equivalent to each other. So whenever we have a cycle in this binary implication graph, we get an equivalence in our formula. So what we can do is just replace all the occurrences of these literals by the occurrence of A, for example. Now the algorithm to actually find these cycles is we use the Tarjan's algorithm. We actually have two copies of the graph, once with negated or with the negative variables, once with the positive ones. They can be mixed, so you can have all the edges between these two. So the point is you just duplicate the vertices, and then you add an edge, a directed edge, whenever you have this, whenever you have a clause, and these should all be ors and not against. So they're clauses. Yes, and then every binary clause corresponds to two edges here in this graph. separated them nicely. This example. So once, so what does the algorithm do? Well, it kind of it gets, or it computes these cycles by traversing the graph, and it will know when it hits a backward edge that you get a cycle. And how do you augment it to get resolution proofs for the fact that literals are equivalent? Well, you add the information of the parents. So just every node gets a parent, and then once you're finished finding with the cycle detection, and you have fixed the representative, that's a very important part, because you always want to derive equivalences with respect to your representative. So, and the representative is kind of independent of the algorithm. So you find the cycles, you fix the representative, and then you compute the equivalences in this graph. And this turns out works really nicely. So when I implemented the thing, I don't think I really understood the algorithm, and I was still able to do it. So kind of cool, I guess. But the main issue then is once you have all the equivalences, how do you handle the substitution into the rest of the formula? And there are basically two ways. One way is you take the fact that A is equal to D, maybe here. This is a two-step derivation. You could leave it at a two-step derivation and then substitute. When you do the substitution, you just take your two-step derivation and plug it into your LRAD proof, and then I claim you don't get a resolution proof, but a RUP proof in general. The point is, if you want to, for example, replace both Q and R in this example with P, then your two-step derivations both use S, and then if you plug them together, it's not resolution anymore. It's still RUP, so it's still a valid LRAD proof in the end, but we want to do better, and the only thing we could come up with, because in general, like, these can be arbitrarily complex, and you would need to know beforehand which, like, how to combine these. So the solution here is to just simply learn binary clauses of for each equivalence beforehand, and then you only have one-step derivations, and they can never interfere with each other. Then you get actually resolution proofs when you do the substitution. So this is nice.
They should have asked this before, but all AND, so that's like.
Yeah, they should be OR. Yeah.
Does this happen like while you're running the target algorithm? Like every time you add a node, every time you determine
once you determine all of the equivalence classes, you have already collected the proofs for all the binary implications. Then you substitute. Then you derive all the binary clauses. And then you do the substitution based on your factors. Yeah. So I think I mentioned all of this. Yeah. And what then? Well, I only showed you two examples, so you do this kind of thing to all of the reasoning steps of the server. You can also use mix and match approaches, like VeryPB supports having RUP steps and all lines interleaved. There's also an approach for SAT where you can do this, and I think CryptoMiniSat supports this format. So now we have LRAD, and well, it's still a lot of work, but we have LRAD. What about other uses? So what other kind of proof logging things are supported in CaDiCaL? mean, CaDiCaL is incremental, so here the main challenge is, okay, support incremental solving in proof logging. The issue is after you've solved your formula, it's always possible to take the final formula and prove it non-incrementally. But this is always feasible, but it's slow, especially if you also want to verify intermediate steps. You need to restart the checker every time, and you get the same issue as if you would have solved the formula non-incrementally in the first place. So you lose all the benefits of incremental solving. And right, so what if you want to do this incrementally and during solving, you need to care about the answers that the solver gives, because your encoding actually depends on answers by the solver. And the thing we came up with is this LEEDRUP or IDRUP format, which also certifies interactions. So whenever the solver says, here's a model, the user kind of gets the model. They will say, okay, I got this model. The solver will claim this was the model, and the proof will check that actually they're the same thing. So you have a user file and a solver file. The solver file will contain all interactions as well as the proof, and the user file will only contain interactions, and then you match them up, and then you can also verify the reasoning in the proof. Okay, now this works with group, and we have seen the talk by Adrian, so you can make this work for any reasoning if you're clever. Right now it only works for group, but you want to do variable elimination. So we have equisatisfiable reasoning for incremental solving, and this is handled by model reconstruction in the solver right now. We can also move it to the proof if we're clever. So VeryPB does this somehow with check deletions, and yeah. Then the way we deal with this issue in our proofs is that we want to have the complete model of the formula in the proof of the original one, so that the way the proof doesn't really know about the equisatisfiable part. So we're fine again. Now, if you're a user of CaDiCaL, how do you get proofs? Well, either in the standalone usage, you just put them to a file, get them to a file, but you can also implement your own tracer with this tracer interface, where you get actually every radical. I would claim it might not capture, or actually no one application which it doesn't capture. So you get all of the proof information, and you can implement all of these proof formats with it. You can do more, so you can extract the proof to convert it or to combine it for a bigger proof, like Tobias Paxian's Max.Server Packers does. So he's doing VeryPB proofs, and he extracts subproofs from CaDiCaL, and he can do this with this interface. We've also heard yesterday that in constraint programming they also use CaDiCaL, so I'm not sure if you're using the tracer interface, but this might be helpful.
We are now. I didn't realize until Matthias taught me Dutch to this is something we could use, but yeah,
that's cool. You can, since these are resolution proofs, you can also do interpolation. Slight remark: if we're doing RUP instead, then interpolation a little bit more involved, because you would need to get rid of the redundancies in the steps. but yeah, we can do interpolation. This one is kind of, it doesn't belong here. You can use the LRAD certificate as a persistent certificate, like we heard. I think Jakob in his talk also mentioned this. This is already used in Lean. They have a verified bit vector solver that calls CaDiCaL and extracts the LRAD certificate. And then they have a verified conversion. And if you don't want to call it CaDiCaL every time, you can just put the certificate instead. Well, we have explainability on the slides. Maybe there are other applications. So we close the loop. We go to VeryPB. What about VeryPB in CaDiCaL? Right now, I'm supporting pseudo-Boolean proof version 2.0. You've seen on a lot of slides yesterday, there's a version 3.0. This one is no longer supported, so I tried current VeryPB check, the current VeryPB checker, and unfortunately, I was not. It didn't read the proof, so it failed on the third line, I think.
It's supposed, I mean, at some point we will keep supporting 2.0. I think.
Yeah, but it should be fairly trivial to change this. I was just I wanted to run one example for these slides with the VeryPB check, but I wasn't able to because of this. Then I'm supporting both DRAD and LRAD variants, so you can do claim root on every step, or you can actually do the poll lines in VeryPB. I'm not supporting check deletions. And I did look into check deletions initially, and well, one thing I always thought is that you couldn't do variable elimination. I learned yesterday that you can. So I have another example. Essentially, well, you can do redundant space strengthening also with check deletions, and you can do it. Not always though. So this, if you have an XOR gate, it's actually sound to only resolve non-gate clauses with gate clauses, but this is not anymore derivable by root, so you need subproofs. So this is slight caveat, and also the subproofs are the reason why check deletion is not fully supported, or was not fully supported at the point where I implemented it.
I think they concluded like you could do it, but you might have to write subproofs. That might be annoying for you.
Yes, and at that point there also were no labels. So my fear was that the subproofs would interfere with the labeling of the solver, and I would need to remap the current like solver IDs to the VeryPB IDs. So I just feared this is a lot of work for something which is it used in is somebody using CaDiCaL and caring about check deletions? I don't know. If you are, please tell me, then I might spend the work and do it, but yeah.
I mean, anytime you're using CaDiCaL, like when you would call it from an optimizer, then you would be very worried about your deletions.
Yes, I don't know how is, I mean, I know that this is inside of Pacos. I'm not sure how they solve this issue, but essentially, so you can tell which, I mean, the solver already maps to redundant and irredundant clauses which correspond to core and non-core sets. So you can do it, and I did most of it. It just when you need subproofs, it's not trivial. Yeah, but this was everything, and it's off time.
So, question for Florian?
So what kind of proofs does CaDiCaL interpolate? You had on one of the previous slides a mention of the CaDiCaL tool, which does interpolation. I wanted to know whether it interpolates anything beyond propositional resolution proofs.
No, it just
No,
does
propositional
resolution.
resolution. Okay, thank you.
Okay, so then let's thank Florian again.